Hello everyone. So this is the re-recording of the session on compact operators. So I had two sessions first, and I forgot to hit the record button, even though I had set up my streaming program. So I'll be recording at least the reminder of the meeting again to post it on YouTube. Hopefully, you aren't too disappointed, and I'm very sorry for that. So anyway, so this was we're entering into chapter 5 on compact operators, which is almost the last chapter. And so we've kind of been teasing what compact operators are in the previous meetings and why they're so important. So we'll finally get to the definition in the book of a compact operator is between two normal spaces. So right now only normal. See that's T, a linear compact linear operator between space X to a space Y is compact if and only if for every bounded sequence xn in X, then the sequence T of xn has a convergent subsequence. So sorry, I have a bit of a cough. So note that in general, if we're in an infinite dimension space, xn being bounded does not necessarily have a convergent subsequence, but here we have the property that at least the image of xn under T must have a convergent subsequence. So this definition of compactness is known as what's known as sequential compactness. There are different ones, and specifically for compact operators, there's another way to define it, which is equivalent, and we'll see we'll actually say this definition as a property. So as a notation, we'll use k of xy to denote the set of compact operators between x and y's, and see a lot of properties about this space of compact operators. First theorem is that, first of all, recall that for infinite dimensional space, compactness is not equivalent to closed and bounded. It's still the case that compactness implies closed and bounded, but the other way around is a bit more tricky. So our first theorem is that for x and y being normal spaces and T being a linear map between x and y, then T being compact in the sequential compactness definition is strictly equivalent to the closure of the edge of the unit ball under T being compact. So recall that the unit ball is just a set of vectors that have norm less than 1. And in general infinite dimensional space, the unit ball is not compact. In the sense that you can always find a sequence of points, exactly unit norm, that does not converge, or at least has no convergent subsequence. So what this is that if you take the unit ball, map it through T, some set, and then take the closure of that set must be compact. Now we won't prove this, but it's actually pretty easy. And actually before looking at examples of compact operators, it's best to look at a couple of other properties. Get to that. One first property is that every compact operator is continuous. In other words, set of kxy is a subset of set clxy being set of continuous operators, which we call that in functional analysis that continuous for an operator just means that it's bounded. So the proof is actually very simple. We know that T is compact, so therefore the image of unit ball closed is compact, which means that this set being compact has to be bounded. So recall that compact implies closed and bounded, so we know that the image of a unit ball has to be bounded as well. And if the image of a unit ball is bounded, that means we can find some m such that the tx under m, and so we're basically pretty easy to you can just take this m as at least an estimate of the norm or the bound for for the norm of t. We know that a compact operator is bounded. Note, however, that so every compact operator is continuous, but not every continuous operator is compact. This is one of the more important one. The identity operator is never compact. And we can see that by taking any orthonormal set in X, so that if we're an orthonormal set, we're immediately jumping to a Hilbert space, or at least an inner product space. So take an orthonormal set with its so they must have norm equal to 1. So we have this bounded sequence of vectors, but it's easy to see that the sequence identity applied to n, which is just un, has no convergent subsequence. So, and the reason it has no convergent subsequence is that we know that for any m and n being different numbers, um minus un, and you take the normal square of that is equal to 2, and so that means that the identity operator here is not compact because this sequence here cannot have any convergent subsequence. So yeah, the corollary is that not every continuous operator is compact, so it's a bit of a bummer, but see that we can get around. Another important theorem is that finite rank operators are compact. So this one is more of a construction result. Okay, how do you construct a compact operator? One very easy way is to build what's called a finite rank operator. So you say that an operator between x and y, here the book says it's a norm space that really should be an inner product space, at least the rest of the proof assumes it's an inner product. You have this map being continuous between x and y such that the range of t, the set of the range of t is finite dimensional, then immediately that means that t is compact. Again, the proof is fairly easy, so since the range of t is finite dimensional, we can take a basis, and so let's take one um, and we'll be a bit more than that. We'll assume that it's even orthonormal. Then we'll construct a sequence xn. We'll just say that it has to be bounded, so its norm must be less than some m for some m. And then we have that the sequence of the inner product txn with ul for n has to be a bounded sequence in R. This sequence being bounded in R must have a convergent subsequence. This is basically first year undergrad calculus. So what we can do is this, we can essentially recursively construct a subsequence xnk such that you have xnk converges. Because we can take here is for each L, so we have to do that for finite number of steps because we have to first construct a sequence such that you have xn u1 convergent, and then out of that one we can extract a convergent sequence for u, etc. Morally, what this means is that finite rank operators effectively map to a finite dimensional subspace where bounded and closed is equivalent to compact. So one of the way, or how do you get a compact operator that will just map to a finite dimensional space. But finite rank operators are useful for more things. So let's give an example of such an operator. Let's take our space to be L2, so the Hilbert space of square summable sequences, but really we could be using any LP space and take some arbitrary matrix size nn, and we will define on our operator that t takes a sequence x1, x2, etc. to y1, y1 to yn, and then all zeros. These y's are just obtained by taking the first n element of the sequence x. This is then a finite dimensional vector, applying the matrix A to it, and we get our first n y's, and so these are the first n elements of our sequence, and all the others are 0. So it's very trivial to see that this operator T has finite rank. In fact, the rank is equal to n, therefore it is compact. Now, another theorem. So we already saw that any compact operator is also continuous, but we have more than that. We have that the set of compact operators is also a subspace, so a linear subspace of CL of XY. Um, Here we're taking both of these as vector space, and so the proof is fairly easy. It's easy to show that 0 to the 0 operator is compact. It's also easy to show that the sum of any two compact operators has to be compact as well, and that scaling an operator also uh, makes it compact. So it's overall pretty easy to prove that. Now, one that's slightly more complicated to prove is that so it's not only a subspace, but it's also a closed subspace. Therefore, it has to contain all of its limits. And the first step is, okay, limits of compact operators are compact, so it's pretty nice. But we'll see that this has very interesting applications. So the proof for this, if you give a brief sketch, so take some sequence of compact operators. Or first, it has to be here we're taking sequence in bounded. Maybe I miswrote. So the idea is that just like we did previously for our finite rank operators, we just recursively construct subsequences. So for take some xn that is bounded, and from which we take yeah, I think here it must be not continuous but compact. Compact. So the idea we start with a bounded sequence. From this we can find some subsequence such that T1 of xn converges. From that we can then extract another sequence such as T2 of xn converges, so on. So for any k we can find a sequence such that Tk of xn converges. We're just building a conversion subsequence, converted subsequence out of our initial sequence. Eventually we get to the end, or at least we get that the tx to so the nth subsequence of x and in this index x n plus 1 has to converge. So the was a bit confused, but the book is a bit clear. The corollary of this is that if T is the limit of a sequence of finite rank operators, here we have to be in a Hilbert space, then T is compact. And this really is the important part, is that finite rank operators, they're basically just matrices, and so we can represent them in a computer, we can think about them as matrices. So what this does is that we can approximate our infinite dimensional operator with finite dimensional matrix. So for this reason, a lot of the numerical applications, for example, PDEs, it's very interesting to have these compact operators because you can take your infinite dimensional problem and approximate it and turn it into just a good old-fashioned linear algebra problem. So to give an example of such convergence, so let's take again that's L2 of square summable sequences and take some lambda n that is bounded in our field. And as we did before in many exercises, we define the diagonal operator that takes an x between x1, x2, etc. Just multiplies it by the terms of lambda. So we have lambda 1 x1, lambda 2 x2, lambda 3, etc. And so for this operator to be compact, it's equivalent to show that the limit of the lambda n has to be 0. And the proof is actually fairly easy. From the limits that goes to 0 to compactness, well, you just build your sequence of truncated operators that are finite rank. And it's easy to show that in operator norm this converges out. And for the other way around, well, you basically have to do a proof by contradiction that, and suppose that lambda n is compact, but that you can find that lambda n does not converge to 0, so you find some epsilon greater than 0 such that the lambda n are always larger than epsilon, or at least in absolute value. And so you can start a subsequence lambda and k such that all of the lambda and k are greater than 0. But then you take your basis vectors, here L1 and L2. This satisfies that, yeah, we have a sequence that satisfies this identity. So, as in many other cases where we wanted to show that something is compact or not compact, we have a sequence that is not Cauchy because any two terms here are greater than 2 epsilon squared, and so it's not Cauchy, therefore it cannot have any convergence subsequence. And so this is a contradiction because we assume that our operator lambda here has to be compact, and so therefore we've shown that the lambdas must converge. Okay, so moving on to essentially the last part, the next rest of my slides are for the second. See on that one. The last property is more of an algebraic one, so we've already shown that compact operators are in our linear subspace of the bounded operators, but we have another thing being that the CL, so the continuous operators on the Hilbert space, are what's called an algebra. So an algebra is just a vector space with a vector product. Here the vector product is simply the composition, and there are quite a lot of examples of algebras in both mathematics and especially in functional analysis, where it's actually quite a big topic, particularly for I believe quantum mechanics. So algebraically, we can say that set of compact operators KH is what's called an ideal CLH. The ideal means here that first of all, zero operator is in KH. We already shown that. Same for the sum of any two operators, compact operators. And we have the additional property that we have T being a compact operator and A being just a bounded operator. Then the product TA, you write this a bit more clear. Have that the product TA, so we have this compact operator times bounded operator, it's also compact, and AT is also compact. So you can think of this as absorbing the your other elements into the sort of the canonical example of an ideal. So we take 2z, so the even numbers. This is what's called, this is an ideal of z, which, so here z is just a field, but you can kind of also think of it as an algebra. Actually, it's not even a field, it's just a ring. Sorry about that. Yeah, so if you're trying to wrap your head around this, just think of the even numbers being essentially also satisfying these properties, but for relative to the integers. We have this theorem that says that for a Hilbert space, then if we essentially this last property, if T is compact and S is bounded, then TS and ST are compact. And if T is compact, then the adjoint T star is compact. And so those are fairly easy to see. One corollary is that compact operators in infinite dimensions are never invertible. The reason for this is that because the identity is compact, if say you had T compact but that was also invertible, so then you could write T times T minus 1. That would be the identity, but then by these previous properties, T times T minus 1 should also be compact. And so since we know that the identity is never compact, T minus 1 here cannot exist. So this was it for the reminders. Again, I'm sorry that I didn't record the last time because we don't have a discussion, which is arguably the interesting part. So hopefully this satisfies a bit. Thank you very much.